right, welcome back to Wired-Tec, everyone. So in our last explainer, we met the ENIAC, right? This absolute monster of a machine. We're talking 30 tons, filling an entire room. It was a massive leap forward in speed, no doubt. But here's the thing. For all that power, ENIAC and computers like it had a couple of major flaws that were seriously holding back the digital revolution.
And that brings us to the big questions for today. These early computers were giants, so why was it so ridiculously hard to teach them a new trick? And why were they constantly breaking down? Well, today, we're going to dig into the two game-changing inventions that solved these exact problems. This is the story of how computing got a brand new brain and a much stronger backbone.
Okay, let's jump right into it. First on the list was what we can call the brain problem. And the issue wasn't just that these computers were huge, it was that they were, well, incredibly stubborn, a total pain to reprogram.
And to really get a feel for this problem, just look back at ENIAC. 30 tons. It's just insane. Inside that metal beast were about 18,000 vacuum tubes. It was an absolute marvel of engineering for sure. But getting it to do a different job, man, that was a whole other story.
So picture this. You've been using ENIAC to calculate artillery tables, and now you want to switch over to, say, forecasting the weather. You couldn't just type in a new command or load a program. No way. A team of engineers had to come in and physically rewire the machine, literally unplugging thick cables and flipping thousands of switches by hand. This wasn't a quick job. It could take days, sometimes even weeks.
And this is the crucial point right here. The program was the hardware. To change the software, you had to physically rebuild the computer. This incredible inflexibility was the first huge barrier, but the solution that smashed it, well, it was one of the most important ideas in computing history.
The solution was the stored program computer. And the idea behind it is just genius in its simplicity. It was this. What if the instructions, the program itself, weren't part of the physical wiring? What if they were just another type of data, stored in the computer's memory right next to the numbers it was working on?
This shift was a total game changer. It changed everything. Instead of a machine built to do just one thing, you suddenly had a universal machine. Changing its job was now as easy as just loading a new set of instructions into its memory. This right here was the birth of software as we know it. This concept, often called the von Neumann architecture, is what finally separated the logic of the machine from its physical construction.
And this idea took off like a rocket. Just a few short years after ENIAC made the rewiring problem so obvious, new machines like EDSA-C in Cambridge were already up and running. They could run all sorts of different programs, making them infinitely more versatile. So just like that, the brain problem was solved.
But you know how it goes. You solve one massive problem and it just shines a spotlight on the next one. Now that computers had these incredibly flexible minds, it became painfully clear that their physical bodies just couldn't keep up. The very components that made them work were also their greatest liability. We're talking, of course, about the vacuum tube. These glass tubes were the electronic switches that made everything happen. But boy, did they come with a long list of problems. They were big, they were fragile, they guzzled electricity, and they got incredibly hot. And worst of all, they were constantly burning out. Imagine trying to keep a machine with 18,000 of them running. It was a maintenance nightmare.
So the world desperately needed a better switch. Something smaller, way more efficient, and a heck of a lot more reliable. The answer wasn't going to be another fragile glass tube. The answer was going to be solid.
And that breakthrough came in 1947 from a brilliant team at Bell Labs. They invented a device that would become the fundamental building block for the entire digital world, the transistor.
This quote just perfectly captures the revolution that was happening. Think about it. A vacuum tube is like a big, hot, fragile light bulb that acts as a switch. The transistor is like a tiny, cool speck of sand that does the exact same job, uses almost no power, and can last pretty much forever. It was the perfect replacement. And it works on a super simple principle. No electric current, it's off. That's your binary 0. You apply a small current, and it flips on. That's your binary 1. By replacing every single one of those big, hot vacuum tubes with a tiny, reliable transistor, computers could finally get smaller, faster, cheaper, and way more powerful. The body problem was finally on its way to being solved.
So there you have it. Computers got a flexible mind with the stored program and a reliable body with the transistor. These were the two breakthroughs that really built the foundation for everything that came next. If you're enjoying this journey through tech history, do us a huge favor and hit that like button, and definitely subscribe to Wired-Tec so you don't miss what's coming.
So, the two great hurdles of the vacuum tube era were finally overcome, but a new challenge appeared pretty quickly. Transistors were amazingly small, yeah, but you still had to painstakingly wire them all together, by hand, one by one. Which leads us to the giant question for our next explainer. What happens when you figure out how to put an entire circuit onto a single piece of silicon? We'll see you next time.